All right, today's topic is an introduction to logarithms. This is a big Algebra 2 topic. So I'm starting off by looking at these exponential equations. So here I see that 2 to the x power is equal to 16. Well, I know that 16 can be expressed as a power of 2. So I know that 2 to the x power is really the same thing as 2 to the 4th power. So right here I see that if my bases match, they're both 2's, then my exponents must match as well. X must be 4. And then if I build off that over here, now I see 1/2 raised to the x power equals 8. Well, again, I can express both of these as powers of 2. 1/2 is really 2 to the negative first power. So it's going to join the x that's already there. So 2 to the negative 1x power is equal to 2 to the third power, right? 8 is 2 to the third power. So now that my bases match, my exponents, they match also. So negative 1x is equal to 3. Divide out that negative 1, and x is equal to negative 3. So I see that I can solve for a missing exponent when I can make my bases match, when they're powers of the same thing. So if we try this one now I see 1/8 to the power of x plus 1 and 32 to the power of negative 2x. Well, these are both powers of 2. 1/8 is 2 to the negative third power. So that negative 3 is going to join the x plus 1 that's already in the exponent position. 32 is 2 to the 5th power. And that 5 is going to join the negative 2x that's already there. So I've re-expressed both of these bases as powers of 2. So now that their bases match, their exponents match also. So I know that negative 3 times x plus 1 in parentheses equals, I'll just say negative 10x. I'm just going to multiply that out. Okay, distribute that negative 3. So negative 3x minus 3 equals negative 10x. Add the 3x to the other side. So I have negative 3 equals negative 7x. And divide out that negative 7. So x would be 3 divided by 7. Okay, last variation. Now I see 2 to the x power equals 20. I'm stuck here. We get absolutely stuck. 20 is not a power of 2, right? I can't express 20 as a power of 2. So here I have to make an estimation. So if I think about 2 to the third power, I know that that's 8. 2 to the 4th power, okay, now that's 16. 2 to the 5th power, okay, well that's 32, right? So I know my powers of 2. So if I'm thinking of what would be a good estimation, well, it has to be something that's in between 4 and 5, right? Because 2 to the 4th power is 16, and 2 to the 5th power is 32. So somewhere between 4 and 5, maybe a little closer to 4. So I could say, well, my estimation is that x is about 4.3-ish. But I really can't be exact, not yet, until we learn more about logarithms. Logarithms enable us to solve for unknown exponents. All right, so now a little practice with just going in between the two formats. So here I'm saying write the exponential equation in logarithmic form. So if I read this, this is 2 raised to the negative 5th power equals 1 over 32. If I write this as a log, I say log base 2, right? That is my base right here in exponential form of 1 over 32. That is called my argument is equal to my exponent of negative 5. Now, if I picture that going back into exponential form, I picture this kind of circular motion. 2 raised to the negative 5th power gets us back to 1 over 32, and it does. That makes sense. next, I have log base 4, right? Whatever is taking the exponent is my base. So log base 4 of 1 equals 0. So log base 4, 1 is the argument, 0 is the exponent. And if I double check that, 4 to the 0 power gets us back to 1. That looks good. Okay, now going in reverse. Can we go from logarithmic form into exponential form? So here again, I'm just picturing this kind of circular motion. And I can say, well, yeah, that is 3 to the 4th power equals 81. Right? 3 to the 4th power equals 81. Okay, here, right, here's my base of 16. So 16 to the 1/2 power, right, it's the same as saying the square root, is equal to 4. Right, base 16, 4 is the argument, 1/2 is the exponent. So 6 to the 1/2 power equals 4. 16 to the 1/2 power equals 4. Or square root of 16 equals 4. Yes, that makes sense. All right, so next we're going to graph an exponential function and its inverse. So here we're starting with y equals 2 to the x power. So let's picture a table with inputs and outputs. I'm going to use x values of -2, -1, 0, 1, 2. So if I take 2 and I raise it to the -2nd power, that is 1/4. And then I have 1/2, 1, 2, and 4. Right? If I look at those y values, they are doubling from stage to stage. So if I plot them, I'm at -2, 1/4, and then 1/2, and then 1, 2, and then 4. Here is my exponential function with a base of 2. Now I'll always have an asymptote, a horizontal asymptote right here at y equals 0. Now I have an asymptote right here because even if I plug in an x value that's way over here, so -12, let's say, 2 to the -12th power is like saying 1/2 to the 12th power. So you're taking 1 and you're dividing it by 2 to the 12th power, something really big on the bottom. So that's giving us a number that's going to be really, really small because you're taking 1 and you're dividing it by a really big number. But it's still not 0. It's very close to 0, but never quite 0. So we have this boundary line, this asymptote that is this boundary line that we approach, but we don't cross it, we don't touch it. We never have a value that we output where the y value is 0. All right, so then here I'm saying, and it's inverse. That's interesting. So inverse. So if we're saying to do the inverse, that means that we want to swap x and y. We want to switch them. So here I'm going to say, well, then I want 1/4 -2, 1/2 -1, 1, 0, 2, 1, 4, 2. All right, so here is the inverse. So if I smooth that out right here, I should be able to see that I have this reflection line at y equals x. So here is a line of reflection at y equals x. So when I have two functions that are inverses, when we swap the x and y values, we see that it's a perfect reflection across the line of y equals x, right? Just a linear equation where our slope is 1. All right, so next I'm saying, well, can you graph the logarithmic function? Can you graph y equals log base 2 of x? Well, I want you to think about that in exponential form. I would say, oh, well, that's like saying 2 to the y power equals x. So if I picture this with a table, then I'm thinking of y as my inputs and x as my outputs. So if I plug in a -2 all the way up to +2 like that, right, then I'm going to output 1/4, 1/2, 1, 2, and 4. And when you look at my table here, hopefully you recognize that it's really this table here, but swapping the x and y values. So this exponential function, y equals 2 to the x, and this logarithmic function, y equals log base 2 of x, these are inverse functions. This is actually the logarithmic function that we're seeing right here. So let's plot it on this graph. So 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2. Okay, I also want to point out that we have a vertical asymptote right here at x equals 0. For the same reason, right here, x equals 0. So no matter what we input for y, even if it's something that is really negative, way down here, it's never going to output a value for x that's 0, right? It will always be very close to it, but never quite 0. So there is my logarithmic function with a base 2. Okay, a few more problems. Can you evaluate? So when I look at this problem right here, it's saying log base 6 of 6. But what it's really saying is 6 to what power gets us back to 6. You can visualize it like that in your head. And we should know that that's just going to be 1. Okay, log base 6 of 1. So 6 to what power gets us back to 1? Well, it has to be 0, right? 6 to the 0 power would get us back to 1. Log base 6 of 1 over 36. So 6 to what power gets us 1 over 36? If you still like the visual, visualize it. 6 to the x power equals 1 over 36. Well, we know that 6 squared would be 36, so this must be the negative second power that gets us 1 over 36. Okay, 36 to what power gets us to 6? Well, I know that the square root of 36 gets us back to 6, so that's like saying 1/2 power if we're thinking exponentially. So 1/2, right? The square root of 36 would get us back to 6. Okay, a few more. All right, can you solve for x? So here 49 to the 1/2 power gets us x. I'm just rewriting this in exponential form. Well, that's like saying the square root of 49 equals x. And the square root of 49 is just 7. So 49 to the 1/2 power gets us x. Square root of 49 gets us x. X is 7. Okay, for this next one, 64 to the x power equals 16. Okay, so here I need to think of how I can solve for x. Can I make these powers of the same thing? Well, yeah, they're both powers of 4. They're also powers of 2. Let's say I do powers of 4. 64 is 4 to the third power. So 4 to the 3x equals 4 to the second power, right? 16 is 4 squared. So now, since their bases match, their exponents match also. So 3x equals 2. Divide out that 3, and x equals 2/3. Okay, for C, here I'm saying log base x of 8 equals 3. X to the third power equals 8. Okay, I want to solve for x, so I can take the cube root of each side, and 8 is 2 times 4, and then 2 times 2. So whenever my index is no longer a 2, I need a group of however many my index states. Here's my group of 3 of the same. So the cube root of 8 equals 2. X equals 2. Okay, last one. So 25 to the x power, 25 to the x power equals 1 over 125. All right, so same thing. I'm going to want to make them powers of the same number. I need the same base. So 25 is 5 squared, so 5 to the 2x. 1 over 125, well, I know that 125 is 5 cubed, so this would be 5 to the negative third power. Bases match, exponents match. So 2x equals negative 3. Divide out 2, and we get that x is negative 3 over 2. All right, have a good day.